If you flip a rock in your garden, you might find a common pillbug, a tiny crustacean, usually no bigger than a grain of rice. But thousands of feet down on the ocean floor, this version of the family scuttles through the dark. The giant Isopod is the size of a football, heavily armored, and reigns as the abyss's most formidable scavenger. This extreme shift in scale occurs across the entire ecosystem. Squids grow to 14 meters long, with eyes the size of dinner plates, while the Japanese spider crab stretches its armored legs across a 12-foot span. Down here, the standard rules of biology operate in reverse, forging familiar animal families into towering, oversized Leviathans. The abyssal zone is a nightmare of physical extremes. The water hovers near freezing, sunlight cannot penetrate the absolute darkness, and the hydrostatic pressure is strong enough to crush a standard submarine. It is also a barren wasteland. Without photosynthesis, the entire ecosystem relies on marine snow, a sparse, slow trickle of decaying organic debris falling from the surface. Logic suggests an environment this energy-starved and hostile should only support tiny, fragile life forms. Building a massive body requires calories that shouldn't exist in a desert like this. Instead, the abyss functions as a harsh evolutionary crucible, forcing animals to adopt giant forms as a baseline for survival. For these creatures, this massive growth begins with isolation. Biologists view the deep ocean as the functional equivalent of a remote island, a closed ecosystem cut off from the rest of the planet. In shallow, sunlit waters, being small is an evolutionary requirement. It allows animals to hide in crevices and dart away from fast-moving visual predators. But in the pitch-black abyss, that survival strategy is useless. Predation pressure drops drastically because hunters cannot see, and the need to stay small and hidden disappears. This relaxed pressure allows species to bulk up. In the Clarion-Clipperton zone, researchers recently discovered entire families of deep-sea amphipods that have freely grown into massive, heavily armored bodies. Total darkness and geographical isolation remove the biological speed limits on growth, allowing evolution to experiment with giant forms. However, a massive body still needs fuel. How do these creatures sustain themselves when there is almost no regular food available? This diagram illustrates Kleiber's rule, which links mass to metabolic efficiency. Notice the side-by-side comparison between the small geometric block and the massive one. The massive block has a lower surface area to volume ratio, which traps heat. While glowing energy rapidly bleeds out of the smaller block, the larger shape conserves its internal resources. In the abyss, a larger animal runs its metabolism at an incredibly slow, highly efficient rate. This efficiency allows creatures to capitalize on rare food windfalls, like a sunken whale carcass. A giant isopod can gorge on a carcass and use its massive bulk to survive for up to 5 years without eating another single meal. In a starved environment, massive bulk is a biological necessity, a critical battery required to outlast years of famine. Energy efficiency is only part of the story. The deep ocean's freezing temperature triggers Bergmann's rule, which slows down all biological development. This slow-motion lifestyle delays maturity and extends lifespans. The Greenland sleeper shark cruises the cold depths for centuries, continuously growing over a 400-year lifespan. This animation shows the physical toll of hydrostatic pressure. In the deepest trenches, the weight of the water column should buckle cell membranes and warp essential proteins. Deep-sea creatures survive this with a genetic hack. Specialized amino acid mutations act as internal scaffolding to reinforce their cells, pushing back against the weight of the entire ocean. These massive bodies are held together by genetic armor, built specifically to withstand the crushing weight of the world above. The dark, cold, and high-pressure conditions of the deep sea provide an unexpected parallel to the hostile void of outer space. Astrobiologists study our Earth-bound giants to predict what life might look like in the subsurface oceans of icy moons like Europa. To map this world, global initiatives deploy advanced submersibles and remotely operated vehicles into the deepest trenches. The pace of ocean discovery is rapid. In a single recent year, international scientists cataloged over 1,100 previously unknown marine species. These giants provide a successful, universal blueprint for biology thriving in the most extreme conditions imaginable. Yet, for all their armored plating and massive scale, these giants possess a hidden biological vulnerability. Because they grow so slowly and live for centuries, they possess almost no ability to adapt to rapid environmental changes. Scientists recently discovered toxic PCBs, industrial pollutants, already accumulating in the livers of the deepest trench-dwelling fish. Simultaneously, rising global temperatures threaten to strip the deep sea of the dense, dissolved oxygen these giants require to maintain their massive sizes. We must protect these fragile Leviathans, or we risk destroying an entire ecosystem before humanity has even had the chance to understand it.